When we picture aviation mechanics, it's all about hands-on expertise with these incredible flying machines. And that's absolutely true.
It is. The skill involved is amazing.
But have you ever considered the silent partner in all that intricate work?
You mean the numbers?
Exactly. We're diving deep today into the fundamental role of mathematics in aviation maintenance.
Yeah, you shared a chapter focused specifically on mathematics in aviation maintenance. Our aim isn't just to acknowledge that mechanics do some sums.
Right.
We're here to explore why a solid grasp of mathematical principles from the ground up is utterly essential for safety, for precision.
Uncompromising safety and precision. That's the heart of it, isn't it?
Absolutely.
Right. Ever stop to think how these massive aircraft stay so reliably safe in the skies? Turns out, it's a lot more math in action than most of us imagine.
Oh, definitely. It underpins everything.
Okay, let's get into it, starting with the absolute basics. Whole numbers. We all encountered 0, 1, 2 way back when. But why are these so foundational in keeping airplanes airworthy?
Well, what's crucial to understand is that even seemingly elementary concepts, like a clear grasp of place value and whole numbers, directly impacts accuracy.
In those critical calculations.
Exactly. The source provides a straightforward example, adding 4,314, 122, 93,132, and 10.
Okay.
If those digits aren't precisely aligned according to their value units with units, tens with tens, and so forth, the resulting sum, which should be 97,578, will be incorrect.
And in aviation, that kind of fundamental error.
It could have significant repercussions. Think weight and balance, fuel calculations, things like that.
Right. And it's the same story with subtraction, I suppose.
Yeah.
That example, 97,564 minus 3,461 equals 94,103.
Yeah, it underscores that even a simple subtraction error, if it involves critical measurements, could lead to serious discrepancies. You just can't afford it.
Makes sense.
Precisely. Then we have multiplication, which, as the source reminds us, is essentially just repeated addition.
Right.
They use a very relatable scenario. 35 cartons, each holding 18 hydraulic filters.
Okay, a practical inventory problem.
Exactly. Multiplying those gives the correct total of 630 filters. An incorrect calculation here could lead to ordering the wrong quantity of essential parts.
Which could potentially ground an aircraft.
Absolutely, or you don't have the part when you need it.
And division is just as vital. That example of distributing 218 landing gear bolts across 7 aircraft.
Right, resulting in 31 bolts per aircraft with 1 remaining. It shows how mechanics need to handle distribution and even account for remainders in practical maintenance tasks.
It's not just abstract math. It's physical parts distribution.
Spot on. And it's worth noting that the material includes Figure 3.1, illustrating place values.
Even the basics are visually reinforced.
Yes. It might seem basic, but it highlights that even these initial mathematical building blocks are non-negotiable for accuracy in aviation work.
Okay, so whole numbers are the base. But then we need to deal with parts of things, and that's where fractions come into play. Numerator over denominator, right?
Correct. A fraction represents a portion of a whole.
Numerator is the number of parts, denominator is the total parts.
Exactly. And as the source emphasizes, there's one absolute rule. The denominator cannot be 0.
Because you can't divide by 0. Mathematically undefined.
Right. No practical application in any real-world calculation.
And we differentiate between proper and improper fractions. What's the key distinction that matters here?
Well, the crucial difference is whether the fraction represents less than a whole. That's proper.
Numerator smaller than the denominator.
Yep. Or a whole number or more, which is improper. Numerator equal to or larger than the denominator.
And that matters when you start doing calculations.
Yeah, this distinction becomes important when performing operations like addition and subtraction, especially when dealing with mixed numbers and measurements later on.
Right, adding and subtracting fractions. That's where the least common denominator, or LCD, becomes essential. Why is finding the LCD so critical?
What's key here is that to add or subtract fractions accurately, they must share a common denominator. You need to be comparing like parts.
Makes sense.
The LCD is the smallest number that each of the denominators divides into evenly. The source gives a simple example, 15 plus 110.
Okay, LCD is 10 there.
Right, so you convert 15 to 210, then add 110, gets you 310. In aviation, think of adding tolerances. If those tolerances are fractions with different denominators, finding the LCD ensures the final calculation is accurate and, safe.
But what if the LCD isn't immediately obvious? Is there a go-to alternative?
Yes. The source mentions that you can always find a common denominator by simply multiplying all the denominators together.
Okay.
For 23 plus 35 plus 47, multiplying 3 times 5 times 7 gives you 105.
It might not be the least common one, but it works.
It works. It provides a common ground for adding or subtracting. Sometimes it's quicker if the numbers aren't too big.
Okay, once we have a common denominator, adding fractions is straightforward. Just add the numerators.
Exactly. For 17 plus 37, with the common denominator already there, the sum is simply 47.
Easy enough.
But consider the panel thickness example, 332 of an inch plus a 164-inch coating.
Different denominators.
Right. Here, you need to find the LCD, which is 64, so 332 becomes 664. Add the 164, and you get a total thickness of 764 of an inch.
And that precision matters in manufacturing or repair.
Vitally. It ensures structural integrity, proper fit, everything.
Subtraction of fractions follows the same principle, I assume. Common denominators first.
Precisely. With common denominators like 1017, 217, you just subtract the numerators to get 817.
Okay.
But when denominators differ, finding that common denominator first is crucial. The aileron rig tolerance example is a prime aviation application.
Oh yeah, control surfaces are critical.
Absolutely. So 78-inch plus or minus 15-inch. Calculating the minimum droop requires subtracting 15 from 78.
Okay, need a common denominator for 8 and 5.
Which is 40. So 78 becomes 3540 and 15 becomes 840. Subtracting gives you 2740 of an inch.
That level of precision in rigging directly impacts how the plane handles.
And its safety, definitely.
Now, multiplying fractions seems a bit different. No need for a common denominator.
That's correct. That's one place it gets simpler. To multiply fractions, you just multiply the numerators together and the denominators together.
Straight across.
Yep. So 35 times 78 times 12 equals, well, 3 times 7 times 1 is 21 on top.
And 5 times 8 times 2 is 80 on the bottom.
Right, 2180.
And the source talks about cancellation as a useful shortcut. How does that work?
Cancellation. It's a great technique to simplify fractions before you multiply. Saves work later.
How so?
If a numerator and a denominator share a common factor, even if they're in different fractions in the multiplication, you can divide both by that factor.
Ah, okay. Like simplifying before you combine them.
Exactly. For instance, in 1415 times 37.
Okay, 14 and 7 share a factor of 7.
Right. Divide 14 by 7 gives 2. Divide 7 by 7 gives 1.
And 15 and 3 share a factor of 3.
Yep. 3 divided by 3 is 1. 15 divided by 3 is 5. So now you're just multiplying 25 times 11.
Which is 25. Much simpler.
Way simpler than multiplying 14 by 3 and 15 by 7 and then reducing.
Okay, and then we have dividing fractions, which involves a bit of a flip, right?
Yes, the classic invert and multiply. To divide fractions, you change the division sign to multiplication.
And then flip the second fraction.
Invert it, yeah. Swap its numerator and denominator. Then you just proceed with multiplication as usual, including cancellation, if possible.
So, for example, 78 divided by 43.
Becomes 78 multiplied by 34.
Okay, multiply across. 7 times 3 is 21. 8 times 4 is 32. So 2132.
Exactly.
The source also gives a more involved example about finding the center of a hole in a plate using mixed number measurements. How do fractions play into that?
That's an excellent illustration of how various fraction concepts combine in a practical scenario. It's not just one operation.
Right. The plate dimensions are 5 and 716 inches and 3 and 58 inches.
Okay, mixed numbers. To locate the center, you need to divide each dimension by 2. But first,
You got to deal with the mixed numbers, convert them to improper fractions.
that's the way. So 5 and 7 16 becomes 5 times 16 is 80 plus 7 is 87, so 87 16.
And 3 and 58. 3 times 8 is 24, plus 5 is 29, so 298.
Perfect. Now, dividing by 2 is the same as multiplying by 12.
Okay, so 8716x 12 and 298x 12.
Which gives you 8,732 inches and 2,916 inches.
Still in proper fractions. Need to convert back.
Usually, yeah, for practical use. 87 divided by 32 is 2 with a remainder of 23. So 2 and 2,332 inches.
And 29 divided by 16 is 1 with a remainder of 13. So 1 and 1,316 inches. That's the center point.
Exactly. And accurate drilling is obviously critical in aircraft construction and repair. Off-center holes can cause big problems.
No kidding. And reducing fractions to their lowest terms, why is that important practical?
It's primarily for clarity and just ease of use. A fraction in its lowest terms is the simplest way to show that quantity.
Less chance of misreading it or making mistakes later?
Pretty much. It makes it easier to understand and work with. The jack screw travel example shows this. Total travel, 1,316 inch, 716 inch in one direction.
So subtract to find the other direction. 316 minus 716 is 616.
Right, but 616 can be simplified. Both are divisible by 2.
Gives you 38 of an inch.
Exactly. Using 38 reduces the chance of errors in subsequent calculations or just when communicating measurements. It's standard practice.
All right, so we've covered whole numbers and fractions. Now, the source moves to mixed numbers, which are, well, a mix of both.
Exactly. A mixed number combines a whole number and a fraction, like 312.
So how do you add them?
When adding them, the source suggests adding the whole number parts together first, then adding the fractional parts.
Making sure you find a common denominator for the fractions, of course.
Always. That cargo area example seems pretty clear. 4 and 34 feet plus 2 and 13 feet.
Okay, so break that down.
You first add the whole numbers. 4 plus 2 equals 6. Easy part.
Got it.
Then you tackle the fractions. 34 and 13. Need the LCD.
For 4 and 3, that's 12.
Right. So 34 becomes 912, and 13 becomes 412.
Add those. 912 plus 412 equals 312.
Okay, but 1312 is an improper fraction.
Right. That's 1 an hour and 12.
Exactly. So you add that 1 to the 6 whole feet you already had.
Gives you a total of 7 and 112 feet.
Precisely. And precise cargo loading is crucial for maintaining an aircraft's center of gravity. So these calculations matter.
Subtracting mixed numbers looks a bit more involved, especially when you need to borrow.
You're right. Borrowing can trip people up sometimes. You still need a common denominator for the fractional parts first.
Always the first step with adding or subtracting fractions.
Pretty much. The bolt grip length example illustrates borrowing well. You have 3 and 18 inches and need to subtract 1 and 516 inches.
Okay, first common denominator for 8 and 16.
That's 16. Good. So 18 becomes 216. The problem is 3 and 216 minus 1 and 516.
You can't take 516 from 216.
Exactly. So you borrow 1 whole inch from the 3, leaving 2 whole inches.
And that borrowed inch becomes
1616.
Yep. You add that 1616 to the 216 you already had.
Making it 1816.
Right. So now the problem is 2 and 1816 minus 1 and 516. Much easier.
1816 minus 516 is 1316.
And then subtract the whole numbers. 2 minus 1 is 1.
So the result is 1 and 1316 inches.
Spot on.
And it was interesting that the source flagged some distractor information in that bolt problem. The overall length wasn't needed for calculating the grip length. Yeah, that's a good point. In complex maintenance manuals or problems, identifying only the relevant information is a key skill. You have to filter out the noise.
Definitely. Okay, precisely. Now let's shift to the decimal number system, which is so common in precision measurements, based on powers of 10, correct?
That's right. Decary refers to 10, likely from our 10 fingers, as the source notes. We use 10 digits, 0 through 9.
And each place to the right of the decimal point represents a decreasing power of 10. Tenths, hundredths, thousandths.
And what's vital here is understanding place value in decimals. Just like with whole numbers, figure 3 to 4 in the source is a good visual for that.
Right, because when adding or subtracting decimals, that alignment is everything.
Absolutely critical. Aligning the decimal points vertically ensures you're adding tenths with tenths, hundredths with hundredths, and so on.
That circuit resistance example highlights this. Adding 2.34 ohms, 37.5 ohms, and 0.09 ohms.
You line up the decimals, fill in zeros if it helps visually.
To get the correct total of 39.93 ohms. Get the alignment wrong.
And the total resistance calculation is off, potentially leading to misdiagnosis of electrical issues.
And for subtraction, like finding the value of a second resistor, 37.272 ohms total minus 14.88 ohms.
Again, that precise vertical alignment is key to getting the correct difference of 22.392 ohms. No shortcuts there.
Now, decimal multiplication has a different initial step. You don't align the decimal points right away.
Correct. That's a common mistake. You multiply the numbers as if they were whole numbers first. Just ignore the decimal points initially.
Okay, then what?
Then, in the final product, you count the total number of decimal places in the original numbers you multiplied.
Total places in both numbers combined.
Yes, and you place the decimal point in your answer that many places from the right end.
So, 0.2 times 6.03. 2 times 603 is 1206.
Right, and 0.2 has 1 decimal place. 6.03 has 2. That's 3 total.
So, starting from the right of 1206, move 3 places left.
Yeah.
Gives 1.206.
Exactly. And the drill wattage calculation, 9.45 amperes times 120 volts equals 1134 watts, shows how multiplying decimals by whole numbers works too.
Okay. Decimal division. Similar to whole number division.
Mostly, but with a crucial extra step if the divisor, the number you're dividing by, is a decimal.
Right. You can't easily divide by a decimal directly.
Well, you need to make the divisor a whole number first. You do this by shifting its decimal point all the way to the right.
Okay, but you have to do the same thing to the number being divided, the dividend.
Exactly the same number of places. You shift the decimal point in the dividend the same number of places to the right. Then you divide as usual, placing the decimal point in the answer directly above its new position in the dividend.
Let's take that example. 0.144 divided by 0.12.
Okay, the divisor's 0.12. Move the decimal 2 places right to make it 12.
So you must move the decimal in 0.1442 2 places right as well, making it 14.4.
Right. Now the problem is 14.4 divided by 12.
Which is 1.2. Much easier to handle.
Definitely. And that means chord calculation for a wing, 262.6 SQO area divided by 40.4 foot span.
Divisor 40.4 is a decimal. Move 1 place right to get 404.
So move the decimal in 262.61 place right to get 2626.
Now it's 2626 divided by 404.
Which equals 6.5 feet for the mean chord, an important aerodynamic calculation.
Often, decimal numbers have more precision than needed, so we round them off. What are the standard rounding rules?
It's pretty straightforward. You look at the digit immediately to the right of the place you want to round to.
Okay.
If that digit is 5 or greater, you round up the last digit you're keeping by 1.
And if it's less than 5?
You just leave the last digit you're keeping as it is, drop all the digits to the right.
Okay. The actuator shaft example, 2.1938 inches rounded to tenths.
The tenths place is 1. The digit to the right is 9.
9 is greater than 5, so round the 1 up to 2 gives 2.2 inches.
Perfect. And the bearing diameter, 3.1648 centimeters to hundredths.
Hundredths place is 6. Digit to the right is 4, less than 5.
So the 6 stays as it is, 3.16 centimeters.
Then the bushing length, 3.7487 feet to thousandths.
Thousandths place is 8. Digit to the right is 7, greater than 5.
So round the 8 up to 9, 3.749 feet. Got it. These rounding rules are standard everywhere, really.
They are. Consistency is key.
Now, convert between decimals and fractions is a frequent task for mechanics you mentioned. How do you go from a decimal to a fraction?
You essentially just read the decimal properly. The place value tells you the denominator.
How so?
For example, 0.52, you read that as 52 hundredths.
Ah, so it's literally 52 over 100.
Exactly. 52 on 100, then you just simplify that fraction if you can.
52 and 100 are both divisible by 4. Gives 125.
Right, so 0.52 is 325.
Okay, that makes sense.
And given that aviation mechanics often work with measurements down to, say, 64ths of an inch, the source details how to convert decimals to the nearest equivalent fraction with a specific denominator like 64.
How does that work? If I have a decimal and need the closest 64th?
You multiply the decimal number by 64.
Yeah.
The whole number part of that result becomes your numerator. The denominator is 64. Then you simplify that fraction if needed.
Let's try that hex head bolt socket size example.
Yeah.
0.3123 inches. Find the nearest 64th.
Okay, 0.3123 times 64 comes out to about 19.9872.
Okay, the whole number part is 19, but it's really close to 20.
Exactly, so we'd use 20 as the numerator. The fraction is 2064.
And simplify 2064. Divide both by 4 gives 516.
Right, so the closest standard socket size is 516 inch. Very practical for tool selection.
And the undersized drill bit example, 0.763 inches to the nearest 64th.
0.763 times 64 is about 48.832. Closest whole number is 49.
So 400, 964 inch. Can't simplify that.
Nope. And the source notes that this means you'd likely use a 34-inch drill bit, which is 4864, as the slightly undersized option. Again, direct application.
And the reverse, converting a fraction to a decimal is usually quite simple.
Yes, that's generally easier. You just divide the numerator by the denominator.
Like 12, 1 divided by 2 is 0.5.
Or 38. 3 divided by 8 is 0.375.
Straight division. What about fractions like 13?
That gives you a repeating decimal. 1 divided by 3 is 0.333. Continuing forever, you usually just round it off to the required precision, like 0.333.
Gotcha. And the source mentions figure 3.6, a chart with equivalents?
Yes, a handy reference table showing common fractions, their decimal equivalents, and often their millimeter equivalents, too. Very useful on the shop floor.
Okay, next we have ratios and proportions, which are all about comparing quantities. Let's start with ratios.
Right. A ratio compares two numbers or quantities, and as the source points out, it can be expressed in a few ways.
As a fraction, like 57.
Or using a colon, 5.7.
Or just using the word 2, 5 to
Yes,
7.
exactly. Ratios are fundamental in aviation for describing relationships between various parameters. They pop up everywhere.
We see them in engine compression ratios, maybe 10.1 wing aspect ratios, 7.1 air-fuel mixtures.
Glide ratios, gear ratios. You're right, they're everywhere.
That glide ratio example is interesting. Aircraft descends 1,000 feet while traveling 10,560 feet forward.
So the ratio of forward travel to descent is 10,560 to 1,000.
Which simplifies. Divide both by 1,000, gives 10.56 to 1, or 10.56.1.
Yeah, clearly illustrates an aircraft's glide performance characteristic.
And gear ratios and speed ratios in aircraft systems another critical area.
Absolutely vital for understanding transmissions, actuators, lots of mechanical systems. The source explains that the speed ratio of two meshing gears is the inverse of their gear ratio, based on teeth count.
Inverse. How does that work?
Okay, say a small pinion gear with 10 teeth drives a large spur gear with 40 teeth. The gear ratio is 10 to 40, or 1.4.
Right.
The speed ratio is the inverse, 4.1, meaning the small pinion gear turns 4 times faster than the large spur gear.
Ah, okay. So if the spur gear turns at 160 RPM...
You use that 4.1 speed ratio, the pinion speed is 4 times 160 RPM.
Which is 640 RPM.
Exactly. Essential for understanding is how power is transmitted and speeds are changed in mechanical systems.
Simplifying ratios, like that airplane cruising speed 200 knots to maximum speed 250 knots.
Reducing 200.250, divide both by 50, gives 4.5. A simple comparison.
And converting a ratio like 9.5 to an equivalent ratio with a denominator of 1.
Yeah, you just divide the first number by the second. 9 divided by 5 is 1.8. So 9.5 is equivalent to 1.8.1. Makes it easier to compare to other ratios ending in 0.1.
Now, a proportion builds on ratios. What exactly defines a proportion?
A proportion is simply a statement that two ratios are equal, like 34 equals 68, or written with colons, 3.4 equals 6.8.
Okay. And the source mentions extremes and means.
Yeah, in the colon form, like A, B, S, C, D, A and D, the outer terms are the extremes, and B and C, the inner terms, are the means.
And there's a fundamental property that makes proportions so useful for solving problems.
The cross-product rule. The product of the extremes equals the product of the means.
So in A, B, C, D, then A times D equals B times C.
Exactly. That's the basis for solving for an unknown value in a proportion. If you know 3 of the 4 terms, you can find the missing one.
Like that example, 6580 equals x100.
Find x.
Cross multiply. 65 times 100 equals 80 times x.
So 6,500 equals 80x.
Divide both sides by 80. X equals 81.25.
Very useful. And the fuel consumption problem. 300 miles on 24 gallons equals 750 miles on g gallons.
Set of the proportion. 300024 equals 750 g.
Cross multiply. 300g equals 24,750.
300g divide by 300. G equals 60 gallons. Practical application for flight planning right there.
Definitely. Proportions are really powerful for solving those kinds of scaling problems.
Moving on to percentages, a very common way to express parts of a whole, particularly in manuals and specs.
Yeah, percent literally means per 100 or out of 100. We see that percent sign everywhere.
Converting between decimals and percentages seems pretty straightforward.
It is. Decimal to percent. Shift the decimal point 2 places right, add the percent sign.
So 0.90 becomes 90%, 0.5 becomes 50%, 1.25 is 125%.
Exactly. And percent to decimal. Shift the decimal point 2 places left, remove the percent sign.
90% is 0.90, 15% is 0.50, 5% is 0.05, 150% is 1.5.
Perfect.
And converting fractions to percentages involves, first, converting the fraction to its decimal equivalent, right?
That's the usual way. Divide the numerator by the denominator to get the decimal.
And then shift the decimal 2 places right.
Yep. For instance, 58.5 divided by 8 is 0.625.
Move the decimal 2 places right, 62.5%. The source then shows how to find a percentage of a number, providing both algebraic and proportion methods.
Right, 2 ways to get the same answer. Finding, say, 15% of 80 defective lights.
Algebraically, of usually means multiply. So 15% times 80, convert 15% to decimal 0.15.
So n, 0.15 by 80, which equals 12. 12 defective lights.
And using proportion, percent means parts out of 100.
So n parts out of the whole, 80, is equal to 15 parts out of 100, and 80 equals 15 100.
Cross multiply. 100 and 215 equals 1200.
Divide by 100, and n equals 12. Same result. Useful for quality control inspections.
Similarly, finding what percentage one number is of another, like calculating motor efficiency, 10.75 is what percent of 12?
Algebraically, n% times 12 is 10.75, or n100, 12 equals 10.75. Solve for n.
Proportionally, 10.75 is to 12 as n is to 100, so 10.75, 12, n 100.
Both methods give you n 89.58%, so 89.58% efficiency.
And finally, finding a number when a percentage of it is known. 80 ohms is 52% of what total resistance n?
Algebra. 52% of n equals 80, or 0.52 n equals 80. Solve for n.
Proportion. 80 is to n as 52 is to 100, so 80 n equals 52 100.
Again, both methods lead to n equal 153.846 ohms, approximately. Very useful for circuit analysis.
Okay, so we've looked at numbers above 0 and parts of numbers. Now, what about values below 0? That's where positive and negative numbers come in.
Correct. Also called signed numbers or integers. Positive numbers are greater than 0, negative or less than 0. Figure 3 to 8 in the source gives that nice visual on a number line.
Adding signed numbers has specific rules depending on the signs.
That's right. Positive plus positive is always positive. Negative plus negative is always negative. You add the values and keep the negative sign.
What about mixing them? Positive plus negative.
Then you find the difference between their absolute values, and the answer takes the sign of the number with the larger absolute value.
Okay. The aircraft weight removal example. Start at 2,000 pounds. Remove a 3-pound component mudded to 3 and a 10-pound component mudded to 10.
So it's 2,000 plus mudded in 3 plus mudded or 10, or simply 2,310.
Which equals 1,987 pounds. Practical application for weight and balance.
Definitely.
And subtracting signed numbers involves a small but important tweak, doesn't it?
Yes, the easiest way is to change the subtraction operation to addition.
And change the sign of the number being subtracted to its opposite.
Exactly. Then you just follow the rules for addition. The Denver temperature example. 52 degrees air on the ground decreases by 20 degrees air at 15,000 feet.
So it's 52 plus 20. Change to addition. 52 plus negative 20.
Now use the addition rule. Difference is 32. Larger absolute value, 52, is positive. So the answer is plus 32 degrees F.
Makes sense, like temperature drops with altitude.
Right. Multiplication and division of signed numbers also follow specific sign rules. Simpler rules, actually.
What are they?
If the signs are the same, positive x positive or negative x negative, the result is always positive.
Okay.
If the signs are different, positive x negative or negative x positive, the result is always negative.
And the same rules apply for division.
Exactly the same. Same signs give positive, different signs give negative. The source provides examples like negative 5x, negative 5 equals plus 25, and plus 10, negative 2, negative 5.
Let's move on to powers and roots, which involve repeated multiplication. Powers, or exponents, are like shorthand.
Exactly. The exponent tells you how many times to multiply the base number by itself. 3 to the power of 4, written as 3 over.
Means 3 by 3 by 3 by 3, which is 81.
Right. The source gives examples like 2 NEO, 2 cubed is 8, and 10 OO is 100,000.
And we use squared for power of 2 cubed for power of 3.
Common terms, yeah. And there are a couple of key rules for powers, like anything non-zero to the power of 0.
That always equals 1. Like 7 equals 1.
Correct? And negative exponents, like 2 arrow.
That means the reciprocal with a positive exponent, so 1 over 2 NEO.
Which is 18, so negative exponents mean fractions.
The source also briefly touches on the laws of exponents for multiplication and division when the bases are the same.
Yes, useful shortcuts. When multiplying numbers with the same base, you add their exponents. Like 3 by 3 OOs by 3 OR is 3 OR.
And when dividing numbers with the same base,
you subtract the exponents, like 10 OR is 10 over 4, that is 10 wires.
Figure 3 to 9, showing powers of 10, is useful here, especially for scientific notation later.
Very useful. Helps visualize the magnitude changes.
Now, roots are the inverse operation of powers. Square roots and cube roots are the most common we encounter.
That's right. The square root of a number asks, what number multiplied by itself gives this number? So the square root of 25 is 5, because 5 by 5 equals 25.
And cube root
asks, what number multiplied by itself 3 times gives this number? So the cube root of 125 is 5, because 5 by 5 by 5 is 125.
Important not to confuse cubing a number with finding its cube root, as the source points out. Like the cube of 27 is huge, 19,683, but the cube root of 27 is just 3.
Very different operations.
And fractional exponents are just another way to write roots.
Yes. A number raised to the power of 12 is the same as its square root. 3 part of 15 is its cube root. 125 then is 125.
The source also mentions figure 310, a functions of numbers chart. What information does that provide?
That's a really handy reference table often found in technical manuals. It typically lists numbers in one column.
And then columns for their squares, cubes, square roots, cube roots.
Exactly. And often it might include circumference and area of a circle, assuming the number listed is the diameter. It usually includes the formulas too, like circumference, AUDA, and area, chart. Saves calculation time for common values.
Moving on, we have scientific notation, a way to express extremely large or small numbers more concisely.
Exactly. Very common in science and engineering. It uses the form A.BC by 10.
Where A is a single non-zero digit before the decimal.
Right. And N is an integer exponent, positive for large numbers, negative for small ones, showing how many places the decimal is moved.
The speed of light, 1.86 by 10 miles per second, or the mass of an electron, 9.11 by 10 areograms, are classic examples.
They are much easier to write and compare them with all the zeros.
How do you convert between standard and scientific notation, say 1,244,000,000?
Okay, you need to move the decimal point, which is after the last zero, to be between the first two digits, the 1 and the 2.
How many places do you move it? Let's see, 3, 6, 9, 12 places to the left.
Right. Moving left means a positive exponent, so it's 1.244 by 10 nibbles.
And for a small number like 0.00000000457.
Move the decimal point to the right to be after the first non-zero digit, the 4.
That's 1, 2, 3, 4, 5, 6, 7 places to the right.
Moving right means a negative exponent, so it's 4.57 by 10 era. Figure 311 illustrates this direction rule.
And converting back, 3.68 by 10 error.
Positive 7 exponent means move the decimal 7 places right, add zeros as needed.
So 3.68 becomes 36,800,000.
Yep. And 7.1543 by 10 arrow. Negative 10 exponent means move the decimal 10 places left, add leading zeros.
Okay, lots of zeros. 0.0000000071543.
Right. And the source notes that operations, add, subtract, etc., with numbers in scientific notation are usually done by converting them back to standard form first, unless you know the specific rules for manipulating exponents.
Simpler that way for most calculations.
Really, yeah.
Now we're getting into algebra, using symbols to represent variables.
Algebra is really fundamental for working with formulas and equations in aviation maintenance. It's the language used to express physical relationships.
Like the basic formula d or e's vxt, distance equals velocity times time, variables representing quantities.
Exactly. Algebraic equations use an equals sign to show that two expressions are equivalent, like the area of a circle, A equals 4.
And there are specific rules for solving for an unknown variable in an equation.
The core principle is balance. Whatever operation you perform on one side of the equation, you must do the exact same thing to the other side to maintain the equality.
So if you have 3n equals 21,
you want to isolate n, divide both sides by 3, n equals 7.
n plus 17 equals 59.
Subtract 17 from both sides, n 22 equals 100.
Add 22 to both sides, n equals 122.
n 5 equals 50.
Multiply both sides by 5, n equals 250. Basic but essential manipulations.
We also see how to solve for a specific variable within a formula, like calculating the total capacitance, CT, in a series circuit.
Right, using figure 312 and the formula 1CT equals 1C1 plus 1C2 plus 1C3.
You plug in the known values for C1, C2, C3.
Calculate the sum on the right side, which involves finding common denominators for the fraction.
Then you have 1CT equals some number. How do you find CT? You take the reciprocal of both sides. If 1CT equals 96.67, based on the example's calculation, then CT equals 196.67.
Which gives CT equals CT 0.01034 microfarads in that example. Shows how algebra solves practical formula problems.
Exactly.
Parentheses are crucial in algebraic expressions. They dictate the order of operations, right?
Absolutely. Operations inside parentheses, or brackets or braces, must always be performed first. If they're nested, you work from the innermost set outwards.
The examples show this clearly. X, 4 plus 3, but you do 4 plus 3 first to get 7, then square it.
Right. X equals 7 in Minolta is 49, not 4 by 3 plus 3 Betterware.
Innermost parentheses first. 93 plus 4 plus 3 is 7.
So it becomes n equals 2 by 3 plus 7 and 9.
Now, inside the brackets, exponents before addition, 7 Amato is 49.
N equals 2 by 3 plus 49.
Now, the addition inside brackets, 3 plus 49 is 52.
Finally, n equals 2 by 52 equals 104. Order matters hugely.
It does, and there's a strict overall order of operations to follow, often remembered by acronyms like PEMDAS or BOTOMIS.
Parentheses brackets.
It's exponents orders.
Multiplication and division from left to right.
Then addition and subtraction, also from left to right.
The source includes a really complex example calculation, n 6254 plus 624 plus 3 plus 10e2 plus 25 plus 42 a4 plus 3 internals, and breaks it down step by step using PEMDAS.
Yes, it's a great illustration of applying the order meticulously. Following those steps leads to the correct answer of 161.34, one step out of order, and the result is wrong.
Essential for complex engineering calculation.
Absolutely.
Moving into geometry now. Calculating the area of two-dimensional shapes. Area is the measure of a surface.
Yes, the amount of space on a flat surface.
Right.
And it's always expressed in square units, square inches, square feet, etc.
Figure 313 provides a summary of area formulas for common shapes found in aircraft design and maintenance.
Yeah, shapes like rectangles, squares, triangles, parallelograms, trapezoids, circles.
Each has its own specific formula using dimensions like length L, width W, base B, height H, radius R, side S.
The source gives practical examples, like finding the area of a rectangular floor panel. A equals LXW, 24 inches by 12, and equals 288 square inches with figure 314.
Or a square access plate, A equals SWIX 25 ends by 25 and equals 625 squared with figure 315.
It also discusses triangles defining different types like equilateral, isosceles, scalene, and right, acute, obtuse, figure 316.
But the area formula is the same for all triangles. A equals 12x base x height.
Correct, using the perpendicular height. The example uses an obtuse triangle with base 2'6" and height 3'2".
Convert to inches first. 30 inches and 38 inches.
Area equals 12 by 30 by 38 equals 570 square inches, figure 317.
Then parallelogram area, A, base x perpendicular height, figure 318. And trapezoid area, A was 12x, sum of parallel bases, x height, figure 319.
The trapezoid example uses bases 14 inches and 10 inches, height 6 inches. Area 12x, 14 plus 10 by 6 is 72 square inches.
Area of a circle, area of engine cylinder bore example, diameter 5 inches.
Means radius r is 2.5 inches. Area x, 2.5 pi raised to 3, 4 and 4 and 6 by 6.25 is 19.635 square newtons needed for displacement calculations.
Briefly mentions ellipse area too, figure 321. And then wing area.
Wing area, AE span x mean chord, is particularly relevant in aviation. The tapered wing example. 50 feet span, mean chord, 6 foot 8 bar, or 6.67 feet.
Area 50 by 6.67 feet, a 333.5 square feet, figure 322. Directly relates to lift.
And understanding unit conversions for area square feet to square inches, multiplied by 144, square yards to square feet, multiplied by 9, is essential for accurate material calculations or comparing specs.
Then we move to three-dimensional solids and calculating their volume, the amount of space they occupy.
Right. Volume is measured in cubic units, cubic inches, cubic feet, etc. Figure 323 has conversions.
The source covers rectangular solids, cubes, cylinders, spheres, and cones, each with its own volume formula, summarized in figure 330 later.
For a rectangular solid like a box, volume V equals its length x with x height, figure 324. Example, 3 feet by 2 feet by 2 feet by 2 feet equals 12 cubic feet.
The baggage compartment examples, 5 foot 6 tons by 3 foot 4 by 2 foot 3, convert to feet first, 5.5 feet by 3.33 feet by 2.25 feet.
Comes out to about 41.25 cubic feet, important for loading limits.
Volume of the cube is simpler. V side equals level of figure 325. Example, 3 foot side gives 27 cubic feet.
Volume of a cylinder is VR, area of the base times the height, figure 326. This has a direct application.
In calculating piston displacement in engines, figure 327 is the volume the piston sweeps in the cylinder.
Exactly. The example uses a cylinder bore diameter of 5.5 inches, so radius r is 2.75 inches. Stroke height h is 5.4 inches.
So displacement for one cylinder, 2.75 by 5.4.
Comes out to about 128.29 cubic inches for an 8-cylinder engine.
Multiply by 8. 126.32 cubic inches total displacement.
A key engine spec.
Definitely. Then volume of a sphere, V43, figure 328. The pressure tank example, diameter 34 inches, so R 17 inches.
V43XX7,
All right.
20,528 cubic inches, needed for capacity or structural analysis.
And volume of a cone, V13 FR 3029.
Again, unit conversions for volume, cubic feet to cubic inches, gallons to cubic inches, etc. from figure 323 are crucial.
They are. You often have specs in different units. Surface area of 3D solids next. This isn't volume, but the total area of the surfaces.
Exactly, like the amount of paint needed to cover it or the amount of material used for the shell. It's the sum of the areas of all the faces or surfaces, measured in square units.
So for rectangular solid, it's the area of the top and bottom plus front and back plus the two sides, formula 2x WX left plus WXH plus LH.
Right. For a cube with side as, figure 325, it's simpler. 6 equal square faces, so surface area equals 6x cents.
The example, 8-inch side cube. Surface area is 6 by 8 minus equals 6 by 64 equals 384 circles.
Surface area of a cylinder is the area of the two circular ends, 2 plus the area of the curved side, which unrolls into a rectangle with height h and width equal to the circumference 2 or 2. So SA equals 2r plus or edge or 2,4 plus 2r.
Surface area of a sphere, figure 328, is 4 baka.
And surface area of a cone, figure 329, involves the base circle area plus the curved surface area, SA shu plus opar plus exo. A bit more complex, figure 330 summarizes these volume and surface area formulas together.
Now we're moving into trigonometry, dealing with angles and sides of triangles, especially right triangles.
Yes, trigonometry, triangle measurement, is vital for various aviation calculations, forces, vectors, navigation, structural analysis.
We need to know the parts of a right triangle. The hypotenuse, opposite the right angle, and the other two sides called opposite and adjacent, depending on which other angle you're focusing on, figure 331.
Exactly. The labels opposite and adjacent are relative to one of the acute angles.
And then we have the three primary trigonometric functions, sin, cosine, cos, and tangent. They are ratios of these sides.
That's right. Remember SOH-CAH-TOA?
Ah, yeah. Sine, opposite hypotenuse, SOH.
Cosine adjacent hypotenuse, CAH.
Tangent, opposite adjacent, TOA.
These ratios depend only on the angle. The source shows finding the sine of a semi-degree angle using a calculator. Sin, 30 degrees equals 0.5. This means in any right triangle with a 30-degree angle, the side opposite it is always half the length of the hypotenuse.
Useful for finding unknown sides or angles.
Very much so.
The Pythagorean theorem, A plus B Euclid C went, where C is the hypotenuse, is another fundamental tool for right triangles, figure 332.
Absolutely. If you know any two sides of a right triangle, you can find the third side using Pythagoras.
Example, find the hypotenuse if the other sides are 7 inches and 9 inches.
A plus B plus C1. So 7 plus 9 plus 9 plus C carry on. 49 plus 81 plus 81 equals C1. So C equals 130.
Which is about 11.4 inches.
And that practical cargo door fitting problem, door is 5.5 feet tall, A by 7 feet wide. B, can an 8-foot square plate fit through diagonally?
Need to find the diagonal of the door opening using Pythagoras. COD in Euclid, 5.5 minutes plus 7 minutes.
C 30.25 plus 49 plus 49.25.
So C uncle is 79.25, 8.9 feet.
Since the diagonal 8.9 feet is larger than the place dimension 8 feet, yes, the plate can fit diagonally. Geometry solves a practical problem.
Exactly. Shows how these principles apply in the real world of moving things around aircraft.
Our journey through math then leads us to measurement systems. We mainly use two, right?
Primarily, yes.
Right.
The conventional system, also called U.S. customary or English system. Inches, feet, miles, ounces, pounds, gallons, with historical, sometimes complex, origins and conversions.
Right. Conversions aren't always straightforward multiples of 10.
And then there's the metric system, or SI, Système International d'Unité.
Which is the standard for science and engineering worldwide, including much of aviation because it's based on decimals. Very logical.
Base units like meter length, liter volume, gram, mass, and consistent prefixes like kilo, centimilli that represent powers of 10, figure 333.
Makes conversions within the system much easier just moving the decimal point.
But in the U.S. especially, mechanics often need to work with both systems.
Absolutely. Aircraft might have components dimensioned in either or both, so being able to convert between them is crucial. Figure 323, the conversion factor table we mentioned earlier, is essential.
Like converting inches to millimeters, multiply inches by 25.4, or ounces to grams, multiply ounces by about 28.35.
Need to be comfortable doing those conversions accurately.
Finally, the source touches on something quite different. The binary number system. Base 2.
Yes, binary uses only 2 digits, 0 and 1. It's the fundamental language of computers and digital electronics.
Relevant because modern aircraft are full of digital systems, computers, black boxes.
Exactly. While mechanics might not do complex binary math daily, understanding the basics is increasingly important for troubleshooting digital systems, interpreting fault codes, or understanding how switches and valves on-off are represented digitally.
The source mentions early computers like ENIAC using it, and it explains binary place values.
Unlike decimal, where places are powers of 10, 1s, 10s, 100s, in binary, the places are powers of 2, 1s, 2s, 4s, 8s, 16s, 32s, 62s, 128s, etc., reading from right to left. Figure 334 shows an 8-bit example.
So how do you convert binary to decimal, say a 1011011?
You just add up the place values where there's a 1 plus some, reading right to left for place values 1, 1 plus 1, 2 plus 0, 4 plus 0, 8 plus 1, 16 plus 1, 32 plus 0, 64 plus 1, 128.
So that's 1 plus 2 plus 16 plus 32 plus 128 equals 179 in decimal.
Oh, correct.
And converting decimal to binary, say 233.
You find the largest power of 2 that's less than or equal to 233, subtract it, put a 1 in that place, and repeat with the remainder.
Okay, largest power of 2 under 233 is 128. Put a 1 there. Remainder is 233. 128 equals 105.
Next largest power under 105 is 64. Put a 1 there. Remainder 105, 64 equals 41.
Next under 41 is 32. 2 a CO. Put a 1 there. Remainder 41. 32 equals 9.
Next under 9 is 8 2Lers. Put a 1 there. Remainder 9 equals 1.
Okay, skip 16. 2 LO over. Skip 2. Come in 2 L. Skip 2. 2 LO there. Finally, 1 2 LO row fits. Put a 1 there. Remainder 0.
So reading the 1s and earlers for the places from 128 down to 1101 1001.
Wow, so 233 decimal is 11M10101000 binary.
Yes. The source gives other examples too, figure 334. It's a different way of thinking about numbers, but fundamental to digital logic.
Wow, okay. That's an incredibly comprehensive mathematical toolkit that aviation mechanics rely on, from basic arithmetic right through fractions, decimals, algebra, geometry, trig, even binary systems.
It really is. It clearly shows it's far more than just, turning wrenches or swapping parts.
Absolutely. It underscores the level of precision, the calculation, the analytical thinking that is just fundamental to ensuring the safety and reliability we expect from every single aircraft.
Couldn't have said it better. The math underpins the safety.
So the next time you're on a plane, maybe take a moment to appreciate that your safe journey is, in no small part, a testament to the power of applied mathematics in the hands of these highly skilled aviation maintenance professionals.
Well said.
It makes you wonder, doesn't it? What other seemingly straightforward fields rely on such intricate mathematical foundations hidden just beneath the surface? Certainly gives you something to think about.